So our next talk, okay, Jiahao, has already shared on the screen. So the next talk is Yao Jiahao from University of California, Berkeley, UC Berkeley. So his talk is Monte Carlo tree search based on the hybrid optimization of variational quantum circuits. So Jiahao, you can start.
Hi everyone. So my name is Jiahao Yao. I'm fifth year PhD from UC Berkeley, and Hao Yao Li is fourth year PhD from Stanford, and we contribute equally on this work. And this is a joint work with Professor Berkeley, Lin, and Professor Yin. So first, we are going to give some introduction about the quantum approximation optimization algorithm, or QAOA. So QAOA was first proposed by Fahy 2014. So it was inspired by the quantum adiabatic algorithm, or QAA. So originally it was the approximate solution to combinatorial optimization problems such as max-hart, and the extension of this QAOA is also called like a quantum alternating operator onset. And the idea is trying to use alternating gate sequence as the generic like a parameterized quantum circuit, or like a variational quantum onset. And so the problems focus in this work, we focus on the problem of the state transfer problems, that is given a initial state phi I, and we want to find a control to reach the target state phi star. And as shown in the graph, so we want to find a control from this point to go to this point on the quantum space. So the problem we're interested in is, for example, the Ising model or the Heisenberg model. And for the target Hamiltonian, we split into two halves. And the initial states are usually the all spin up states or spin down states. Those are states very easily to prepare in the lab. And the target states are the ground states of the target Hamiltonian we are interested in. The QAOA onset is shown here. So the QAOA onset is trying to alternating between the two H1 and the H2, two Hamiltonians until the P steps. So the energy or the fidelity are the quantity we care about, and the energy is defined as the like expected energy, and the fidelity is the overlap between the two quantum states, the target quantum state and the evolved quantum state. For the optimizations, what we do is we try to minimize the energy or to maximize the fidelity. Another introduction I'm going to give at the very beginning is about reinforcement learning. And the main building blocks in the reinforcement learning is called MDP, or Markov decision process. And there are four ingredients in this MDP. First is the state space. And at each state space, each agent can act choose the action from the action space. And in this case, the agent can choose A or B. So another ingredient is action. And so at a certain state, the agent chooses certain action, and with certain probability, the agent will land to another state. This is also induced by the transition probability, P. So after all this environmental transition down, the agent will get the reward, defining like whether this action is good or not. So the total goal of the agent or reinforcement learning is trying to maximize the total expected reward in order to find the best policy to get higher reward in this case. So the first work along this line is called the PGQAOA, or the policy gradient-based QAOA algorithm. It's trying to learn to get the good sequence of the action. So the onset of the problem is shown here. So it's the original, the QAOA onset. And the difference is we're trying to parameterize this parameter alpha and beta using the policy network. And for the policy, as shown in the figure, it can be the very simple policy, it's the Gaussian policy. And at each training step, the agent trying to sample the action from the policy. When you get the alpha or the alpha and the betas, then the agent aggregates all the alpha and the betas together to perform the quantum evolution either on the quantum computer or on the quantum simulation. And the agent is given the reward for each sample. And the reward is feedback by performing the policy gradient update to the parameters of the policy network. And when the agent keeps doing the policy gradient updates, the reward get by the policy, induced by the policy, is higher and higher. And the result is showing on the next slide. So we benchmarked our PGQA algorithms on this non-integrable many-body qubit chain, and with other like a black box optimization. And we can see for the PGQA across different sizes of the model and the different strengths of the noise, the PGQA performs the outperforms other like a black box optimization. Also, we go on to test these algorithms on the more realistic experiment setting, and mostly are the constraints given by the hardware, like the word clock time, including the network latency or the circuit batching. And so we can see in these experiments, the PGQA is also robust to noise and outperforms the previous method in these more realistic setups. And this algorithm is already integrated into the Google software research stack called Research. And if people are interested, they can go to this repo to get more detail of this like algorithm. So we introduced the QAOA algorithm or QAOA onset, and now we want to go think whether we can go beyond this onset. And we coin a word called generalized QAOA onset. So that is at each time step, you can also choose different gates and choose the duration you apply to the gate. As shown in this formula is tau and alpha. So when we introduce these two parameters, it's naturally introduced two different class of parameters. One is a discrete parameters that's calling which gates you want to apply, and also the continuous parameters, which means how much duration you want to apply for each gate. And also, we have some assumption for each gate. That is, for each gate, we think them they are coming from the fixed Hamiltonian pool called this A, and we also limit like the nearest gate cannot repeat each other. Otherwise, we just merge them together into a smaller onset. So the nearest neighbor cannot equal to each other. And the total possibility possible like a sequence under this onset is growing exponentially, which lets the exhaustive search intractable, and we must come out with a good optimization method to solve this problem. So the natural questions followed by this like a generalized onset is these two, like how to choose the right Hamiltonian pool and how to find the right optimization problem. And we are going to dive into these two problems like one by one. So for the first question, so we want to choose a Hamiltonian candidate pool that can be large because we want to increase the expressivity for the onset. But we don't want it to be too large because because we don't want it to be very computational, like expensive. Also, the optimization problem will be more difficult. And for the optimization problem, it's very naturally. It's very naturally like involved two categories of optimization. One is the discrete, another is continuous. So discrete one is which gate you want to choose, and the continuous one, we also want have other properties. Says, can we do it in a graded derivative free approach, or can we do in a noise robust approach? And the following discuss is all about these two questions and also the sub questions. So first is about the generalized QALN onset. So for every local operator, we define it in this way. So it has the three elements. So the first element is the coefficient constants for this local operator called J, and also the I means the set aside the operator is acting on, and the gamma or Y is the different types of operators. So if you define the type of operator and the size of the operator atom and the coefficient, you get the local operator. And for any Hamiltonian, it's actually the summation of these local operators as shown here. So with this notation, it's very easy to define any kind of gauge as the one example is shown here. So we're trying to generate a Hamiltonian by one to enumerate all the possible Hamiltonian, and two is we're trying to complete the Hamiltonians by symmetries. So say the translation symmetry, the spin symmetry, the Z2 symmetry. So any symmetry we're trying to complete by that. So this is our way to generate the Hamiltonian pool, but on the literature, there are also other ways to generate that. So which is called the cubic adaptive VQE. So where they propose a minimal complete pool shown here, and so this is not the focus of our work, but we just list here by passing. And actually, our way to choose the Hamiltonian pool is based on this CD driving or counterdiabatic driving theory. It's coming from the physics literature, and the goal is actually not very difficult. It's trying to introduce the auxiliary counterdiabatic Hamiltonian drives on top of the target Hamiltonian in order to suppress all the transition between the eigenstates. So which means for any state, so if we have the time-dependent Hamiltonian, so originally it's evolved with this a time-dependent Schrodinger equation, and the techniques using the CD driving is we want to go to the moving frame, and we want the Hamiltonian to remain stationary on that moving frame. So where we introduce another unitary transformation U, it's trying to diagonalize. It's trying to diagonalize the intertenuous eigenstate for the Hamiltonian. So if we introduce another wave function under this transformation called phi theta, it's actually satisfied this effective Schrodinger equation. So which means if we denote this part as the effective Hamiltonian, so that means the original Hamiltonian we want to subject an actual term, and it's give you a effective Hamiltonian. On the other hand, that means if for the original Hamiltonian, if you add this Hamiltonian back, when you go to the moving frame, your effective Hamiltonian is actually equal to this H naught. So which makes it like a stationary, and no transitions will occur under this moving frame. So to sum up, for this transitionless driving, so we get a counterdiabatic driving Hamiltonian as the original Hamiltonian at this actual term. And I will also give you some more intuitive explanation of what the CD driving is. So for example, like waiters want to serve the water. The goal is to deliver the water to the table with high fidelity, and high fidelity here means without stirring out the water. And so one way is the glass is served vertical at the very beginning and also at the very end of the process, and all the process between the glass is vertical. So this way is this also is actually the analog of the adiabatic driving, so which moves slowly, and at each time the wave function remains the eigenstate of the Hamiltonian. That's what counter-diabatic driving is. It's a waiter trying to tilt a plate, and in order to counter this this actual force given by this acceleration. So in this way, the waiter can serve the water faster and also with high fidelity, so without the water spilling out. So if we work out the formula here, we can safely focus on like a pure imagining Hamiltonian. So because for the single qubit case, so you have sigma z plus lambda sigma x. So if you derive the terms, the gauge potential or the counter-diabatic Hamiltonian term, there will be sigma y. And for a more sophisticated case, it's like a spin chain. There, you can derive this like a counter-diabatic terms by like a first order approximation. You'll give the sy, and also the higher order term like a xy, xy and the yx, also the zy and the yz, and so on. So for example, for in the spin chain case, if we first two terms is coming from the original Hamiltonian, we split into two parts, and all the H2 and the H4 are coming from the terms from this CD driving term. In this way, the CD driving gives us like a three actual Hamiltonian, and we put them into the generalized QAOA ansatz in order to make our ansatz more expressive. But yeah, again, the problem here is it's a hard problem because it's like exponentially growing. So when with respect to the number of this Hamiltonian pool. So also if you use our techniques defined in the paper, you can also generate more like a Hamiltonian, like a gauge potentials for like a spin 1/2 or other spin 1 Hamiltonian with different symmetries. So which we won't dive into details, but we can put. So this part is only show we can put more like a sophisticated Hamiltonian into our Hamiltonian pool, and this approach can be based on the CD driving. All right, so the thing we are going to talk first is there's a first to solve the problem is how to deal with this like a generalized QA ansatz called CD QAOA. So you have this generalized QAOA ansatz, and the expectation energy is your objective. Then you have the two like a bi-level optimization. One is you want to solve this inner optimization, and also the higher like a level optimization in order to find a discrete policy. So in that way, in the original approach, we use the autoregressive network, and it's usually for the discrete optimization. So that is when we want to parameterize the neural networks to model this conditional probability. That is, so each xi given by all the history of the x. So all the x like smaller than I. And this kind of, I have to emphasize like this kind of neural network, autoregressive network, already have a lot of application in physics. People use it to solve the statistics physics problem and model wave function and also like a quantum simulation. And it's also can very easily to extend to very sophisticated neural network called RNN, BERT, or GPT or transformers. So yeah, and so we use this autoregressive network here to parameterize our policy for the discrete one. So like at each time step, you are like a sample an action from the discrete policy, and then you feed back this action to your autoregressive network. You get the second like a conditional
recording
probability.
stopped.
you get the second probability. And for the third step, you post all your previous action, and you get another action out. Then for our like policy updates, you first need to we want to maximize the total reward, and the reward here is defined as if it's 0 in the
recording in progress,
and you get the energy only at the end, because the measurement shouldn't happen in between. And we also add the entropy bonus in between, entropy bonus to the function to the reward as shown here. So in OR, so our like a CDQA-OA approach is trying to use this like a collaborative autoregressive network to give you the policy, parameterize the policy, and you use the solver to get another continuous parameter, and do the PPO updates to get another update for the parameter of the network. And in this figure, we showed the performance of this generous ansatz. It's quite powerful compared with the QAOA ansatz, because if it's only use the Q equal to 3, like a 3 length, it can beat the QAOA with Q equal to 8 ansatz. And the following on work on this line is we trying to merge the two policy into together, which called the IOQAOA, where the autoregressive network trying to parameterize the both discrete and continuous parameter. So we so on top of each autoregressive layer, we emit two head. One is one parameterized continuous, one parameterized the discrete one. And it's also performed the autoregressive sampling, and we aggregate all the parameters together and perform the PPO updates to the parameter to get the policy updates. And we also show the result here, and we can see in presence of the noise, the IOQAOA always like outperform the previous work like CDQAOA, which is not noise robust. Also on different kinds of the model, like the Heisenberg spin 1 models, and where also like more models here. So here the catch is, so we parameterize this hybrid continuous and discrete policy, and in an autoregressive way, and it's quite agnostic to the physics source of the noise, and so which is better than the previous like CDQAOA, and also it's quite versatile to make it to adapt to different setups. However, we find there's one fitting mode for this IOQAOA algorithm, so which is shown in the figures. So when we try to add more function evaluation to IOQAOA, we find the energy ratio or our objective kind of saturates at some point. And when we increase the function evaluation, the number of the unique gate sequences is plateaued at some point. So which means at some point this QAOA didn't exploit to other kind of like a gate sequence. Also showed in this like a histogram here. So we are finding here like IOQAOA tend to like exploit some suboptimal like a local optima. And for the continuous optimization, because the IOQAOA really like a joint optimize both like a discrete and continuous optimization. So for the continuous, it's also do a very rough optimization. So that's because of the joints like a couple effect between the discrete and continuous optimization. For this IOQAOA, it's trying to like find this failing mode. So
need one.
Can people hear
okay.
me? Can people hear me? Can people hear me? So
yeah, we can hear you. Yeah, we can hear you now. We can hear you.
sounds good. Sounds good. So that's we need an algorithm which have the better continuous solver. So which means we can get reliable and accurate results. Also with better exploration, which means we can get out of this local minimus if the algorithm stacks in some. So that's why we proposed a new method called Monte search-based QAOA optimization. So we have the two loop optimization. So which is the inner loop? It's focused on the continuous optimization, which use a policy gradient to perform the solver in a noise robust way. And it also have the outer loop, which perform the discrete optimization, and it's based on the Monte tree search. And the reward obtained is then backpropagated through this tree search through this tree, and in order to improve this tree policy. So we are going to dive into these two optimization one by one. So for the outside one, for the discrete optimization, Monte search is really like a giveaway to strike the balance between the exploration and the exploitation. And it's also leverage the statistics in the search trees so that it can get rid of the local minima if it's if it's trying to explore another part of the tree. So for the detail of this tree is we keep track of the two quantities, which is the number of the selection of the action at each state and also the expectation reward for each action at each state. So the details of this Monte search algorithm is shown as follows. So for the discrete optimization, at each time, it's trying to form the searching path. And when it finds a searching path, it finds a node which is not fully expanded. And if there's a node is not fully expanded, and the Monte search will try to select a node according to this UCB bound. So the first part is the average score, and the second part is actually the exploration effect for the tree policy to visit other unseen unseen protocols. And we also trying to evaluate at the end of this rolling out, we evaluate every a terminal state by the quantum computer or quantum simulator, and we backpropagation this a reward to the Q and to the N along this tree line. And inside, we also have the continuous optimization called the natural policy gradient. The goal is to trying to find the optimal duration for each a state, a tau 1 until tau q. And the solution there is trying to use a policy gradient to solve this constraint optimization. And the details in this policy gradient, so we use first we enforce the constraint by first perform a sigmoid on top of the Gaussian policy and to normalize them. And we also add another entropy bonus as a regularizer to our report. So the total objective is for the reinforcement learning is shown at here. And so we also compute the Fisher information and perform the natural policy gradient to update the parameters in for the continuous optimization. So in terms of this performance, we can see for the Monte search QAOA, it's actually fixing some issues for the IO QAOA. So especially for the large T regime. So which means more challenging to the hybrid optimization because the time is larger and it needs to do more do more optimization there.
So we can see the orange line is the Monte research, and the blue line is the IOQAOA, and the performance is getting worse in, say, like Ethan 1D and LMG models when the time gets larger. So and that is also the phenomenon we mentioned at the beginning of this Monte research algorithm, and so we also trying to look at the landscape for the discrete protocols. So we focused on the LMG model and just selected 3 different setups, like a T equal to 500, 1K, and 1.5 thousand here. So if we look at one interesting plot, say the 1.5 thousand here, we can see it's actually when the continuous prime optimizer solve the problems with high quality, the good protocol for the discrete one is actually not small. It's actually had plenty of the protocols in our histogram plot. But as we also showed in this figure, we have the inset here, so which we show the IOQAOA is the optimal one location. So it's actually finds a small bump at around the 0.5 fidelity here. So this is also verify our assumption IOQAOA, because it's optimized both continuous and discrete together, and sometimes the optimization for both is not doing well, and due to this coupled reason, and it's trying to fail. And for the Monte research QAOA, it's actually mitigates this effect coming from this a joint optimization, and can always find a near optimal solution here. So yeah, so this is our results showing Monte research approach can outperform the IOQAOA one. Also with presence of the noise. So let me try to wrap up the today's talk. So today we proposed ansatz called generalized QAOA ansatz, so which is more expressive, but also raised a lot of challenges in terms of how to do the optimization and how to select the Hamiltonian pool. So in terms of the optimizations, it's for the discrete and continuous hybrid optimizations, it says for the reinforcement learning, it actually shows a lot of versatile for this task, and also noise resilience in different kinds of physics source of noise. For the Hamiltonian pool selections, we not just selected from a random choice of the operators, and those operations are based on the variational counter-diabatic driving. And also we trying to compare the method we have developed here. So between the CDQAOA RL1 and the Monte research. So for the CDQAOA, it's actually a bi-level optimization, but the back shortcoming of that is it cannot become a noise robust optimization. The difference of the IOQAOA and the Monte research, for the IOQAOA, it's actually do the joint optimization on top, but Monte research QAOA, it's trying to overcome the shortcoming, especially the challenging mode like a larger T regime for the IOQAOA, and also can handle different kinds of noise in a noise robust way. So the recap for the Monte research is, so it is very efficient to it provides an efficient way to do the exploration, and very robust to different kinds of noise. And Monte research QAOA shows the superior performance in a large duration regime, which is very challenging for a hybrid optimization quantum algorithms. And we also find another interesting phenomenon. which shows that there's a large proportion of the gate sequence with a high energy ratio, given that the continuous variables are solved with high qualities. So in terms of future works we are going to work on is we are going to carry out a more fair comparison against a gradient-based method, because the method here we talk about is a derivative-free method. And we also want to extend this to a more like advanced physics system, say the Fermi-Haber models. And again, we also want to test our models on the more realistic noise of the model, with more realistic noise models, say on the IBM or Google's quantum computers. Another line we're also interested in, like a more powerful neural network ansatz, say the recurrent network, self-attention layer, or transformers neural networks. And in OR, we also want to find out a more generic way to get the Hamiltonian for our setup. So with that, so this is the joint work with Jiahao Yao, Martin Booker, Lex Ning, and Professor Ling Ling. And we also have our list our software and the papers here. And thanks for the organization, and thank you all for listening.